All right. I think we are live streaming this morning. Well, morning for us anyway.
Yeah. Hey everybody. Hope you can hear us. Please let us know or write something down in the comments. If you can hear us, just checking the audio. And for those of you who are here, welcome to the second episode of the Pine Research YouTube live stream Q&A, which has now been renamed Echem Office Hours. We're your host, Dr. Alex Paroff. I'm Alex Paroff. He's Dr. Neil Spinner.
That's correct.
And we're excited to be with you today. And the goal of this Echem Office Hours is to just try to answer as many questions as you have about electrochemistry. We get a lot of them through our webinars and YouTube videos, phone calls, emails, things like that. One thing that I just want to mention ahead is that you've noticed that we've posted this waiting video before the live stream starts, and we're hoping to have more of these, but during that waiting video, you can post any and all questions that you might have. Neil and I will start to answer those questions through the chat, but you can also ask us questions from the YouTube community posts that we usually put up before the live stream. So we're going to answer the chat questions just in the order that we receive them. And generally, we give a little bit of priority to our YouTube members first. But for those of you who are watching this live stream after it's ended, I'll add a timestamp in the video description so you'll know which questions were asked at what times, and then you can go to it later. Also note that this is we're using Zoom as kind of the broadcasting platform for Echem Office Hours. So we've noticed there's about like a 20-second delay between when you mention something and then we respond. So just keep that in mind when we're talking back and forth through the chat and when we answer your questions. We do want to give a shout out to our YouTube members who are joining us. Thank you so much. And also, we just want to say a couple of the things we want to share that you can ask any questions at all. Electrochemistry is a very difficult subject, and there are no stupid questions, no matter how you may feel or how they sound. So feel safe to ask any and all questions. We're aiming for this to be between like 1 and 2 hours in duration. Of course, if it goes a little bit longer, we will try to answer them. And then lastly, we will apologize in advance if we mispronounce anybody's name. So that is all I wanted to say. And then let's just check to see if there are any questions from the chat on for
doesn't look like there are any yet, but go ahead and start posting any if you have some. We have a couple prepared because we do have plenty of questions, I suppose, that we've gotten over the months and years of doing our job and doing other events and things like that. And I've done webinars for those who might be aware over the past couple of years. And in many of those webinars, there's been a lot of questions. And so I've tried to answer those live during those whatever question part at the end of the webinar, but I don't always get to all the questions. So let me start maybe with one question that I have here that I do have prepared. Let me sort of adjust some things here for you. So get going a little bit here. So this was a question I got some time ago. It's kind of a general question, but it's one that a lot of people do think about, especially when we're talking about impedance data. And so the question is generally that should the axes be orthonormal when reporting Nyquist data or Nyquist plot from impedance? And so I'll just kind of show a little bit of impedance data and talk about orthonormal plotting conventions here so that you can see the effect of this. So my general answer is yes, that when you're reporting Nyquist plots, you do want to have orthonormal axes. Now, what orthonormal means is that the scale on your X and Y axes. So before I show some actual data, this is a Nyquist plot. You have Z real down here, and you have typically Z imaginary or minus Z imaginary here. And usually you get stuff like, you know, some semicircle, okay? What it really means, and this is also a misconception, so I'll try to clarify this as I do it. What it doesn't necessarily mean is that, for example, we start at 0 and we go to, you know, whatever 100, whatever, you know, unit or we have here. It doesn't necessarily mean that this also has to go to 100. That is not necessarily what it means. Either of the axes can have different ranges of values. This could go to, looks like maybe 200 or 175, something like that. So you can have different like lengths of axes, but what it means is that the number of pixels, literally like pixels or inches or meters or centimeters or nanometers, whatever you're looking at, whether it's on a computer screen or on a piece of paper, that these distances are identical. That's all it means. Okay. So, you know, basically everything makes a perfect square of units. Whereas normally you can, you know, you can condense one axis on a plot normally. And, you know, there's nothing wrong with doing that because you might have a, you know, different scale on the x-axis than you do on the y-axis or something like that. So with orthonormal, that's not necessarily the case. So here's an example of a Nyquist plot. Yeah, this is a lithium-ion battery data, just as my kind of convenient example here. And in this case, what you can see is that it is not orthonormal. Okay, so I'll zoom out a little bit. You can see the full Nyquist plot here. It's not orthonormal. Okay, now, just like I said, I can zoom one axis, zoom in or out. I can zoom another axis in or out, right? This is just normal plot behavior. Okay, now in our software here, we have this button, this orthonormal button, and I can toggle it to make it orthonormal or not. So you can see I'm toggling between. Now, when I am in orthonormal, when this button is activated, I can't zoom just one axis before like I could. I can zoom the whole thing in and out, but I can't zoom just one axis, okay? But what I can do, for example, is I can move one axis up and down. So this is how I can show you like the, you know, the length of the x-axis, just because of the window that I'm showing here in my screen is wider. So the axis on the x, in the x-axis, the Z real axis has more, you know, length and range to it. Then the y-axis also, this one starts at 43, this one starts at -18. So they don't have to start at exactly the same number. So that's one of those things about orthonormal that people do, I think, get confused about. It's like, oh, I have to start at 0, 0 or 10, 10 or something. That's not the case necessarily. It's just that the distance, you can see that if, you know, for example, I were to draw like anywhere between the same, it's a perfect square, in other words, right? Like this is exactly whatever that, what is that, 13 or 12 point, whatever, like the, you know, exact number of ohms is here with this many pixels on my computer screen is the exact same number of ohms and pixels in this direction. So everything makes a perfect square. So that's the point of the orthonormal. And then the reason why you do that is really because in a Nyquist plot, primarily the features you're looking at have distinctive shapes, distinctive patterns, and things like semicircles or lines going off at low frequency or even at high frequency. In this case, you see there's a really strong inductive kind of a tail, which is typical for a battery experiment. You can't really easily tell. I should word it this way. You can really easily tell something about your system if you have orthonormal axes. Okay, and so this semicircle right here seems like it's not perfect, right? It's a little bit like squashed down. So you may have seen some of my other webinars. I've talked about constant phase elements and things like that. So for example, if I were to draw a perfect semicircle, which this is also not really perfect, but let's just say this is like perfect semicircle. You can see that this is like squashed down. It's not ideal. And so I can only really tell that because my axes are perfect orthonormal, because they're square. So if I have a circle, if I were to draw a circle or a semicircle, again, pardon the artistic inability here, but it would look perfectly. Whereas if I zoom or squish, one axis, but I expand another axis, my circle will start to look like an oval, but it's just because I'm looking at it strange. It's not that it is or isn't ideal. And so what I'm doing with this orthonormal is I'm giving myself the ability to quickly see, is my semicircle a perfect semicircle or not? It also allows me to see the angle of this low frequency part. So you see this is about 45 degrees. So I say, okay, I have some infinite Warburg diffusion in this tail. But if it was perfectly straight up and down, that would be a capacitor, and something in between, you have some other information. But the point is, if I don't have orthonormal on, I can't tell any of that kind of stuff. So right now, this looks really non-ideal, really squashed, right? Well, that's just because my axes aren't orthonormal. So what I could do is I could scale this axis. Now it looks perfect, but it's not. I just scaled one axis. So I'm not really giving myself the ability to tell exactly the level of ideality or the kinds of things or conditions that are going on when I'm allowing my axes to be scaled like this. And so the last thing I'll say about this is something I used to actually feel when I was in graduate school. I had this I've completely reversed my position. So you can change your mind. That's what scientists do. We change our mind in the face of new information. And in my case, the new information was everything I just talked to you about. It's like, oh, I can get a ton more information if I have orthonormal axes. What I used to think, and why some people do occasionally prefer to not have orthonormal axes, is because you can fit everything in the screen, right? When we plot, data in our publication, in our paper, in our presentation, we want to fill the white space, right? We want to have all of our data in one tiny corner with a bunch of blank space. That's sort of bad form. And one of the consequences of orthonormal axes is exactly that. I have all this empty space. Now I could, if I'm publishing this data, I can do things like, decrease the, people.
Hey Neil.
Yes.
Question. Are you using Aftermath right now?
I am.
Oh, okay.
Have I not sharing?
You're not sharing.
Have I not been sharing this whole time?
No, you've only been sharing the PowerPoint. So I'm like,
God.
oh, well,
Wait a second.
we're really looking at this.
You should have interrupted me sooner.
I've
been sharing.
I just thought you were.
No, oh my gosh. Yeah.
I was like, oh,
I didn't change the application.
Yeah.
I shared the PowerPoint and not the application. Good grief.
Oh no, it's all good. It's
Good
all good.
grief.
After you're done, we'll get to
bad.
today's question.
Oh my gosh.
But it's good to hear from.
See, this is these are the things that you get to enjoy is the troubleshooting of absolute inability to work simple programs.
Yeah, don't worry, we're switching to Neil's gonna switch to Aftermath, and
I've got it going now.
Yeah.
So if you're hearing this, you should hopefully be seeing it. So everything I just showed you was not captured on it. So I'll try to do a bit of a quick recap. Everything I just said, which I said stuff while I was showing all of this, and you didn't see any of it because I'm really bad at this software, apparently. Oh man.
It's all good.
Yeah. I'm usually sharing screen, but I shared the PowerPoint application or whatever. It's brilliant. Absolutely brilliant.
All right.
As you can tell.
Start over. We're good.
Yeah. Orthonormal axes are really important. So this is what I was showing while you couldn't see it, right? See how the blank space when you have orthonormal axes? That's one of the problems, right? Now I can adjust the axes of this, to eliminate that space, which is what people tend to do in publications, for example. But this is one of the arguments for not restricting orthonormal axes, is you get all this blank space and there's nothing you can do about it. You can't just, zoom the x-axis in or whatever, because then it would get distorted. You can center it or whatever, but that's about all you can do. So this is why, for example, like as I said, when I was in graduate school, I used to kind of be like, I don't want to orthonormal my axes, it's fine. And if I want to tell how ideal my data is, I could just do a circuit fit, and that'll give me, CPE and alpha and all this different stuff. So it's like, I think that since I was in graduate school, not only has my opinion changed, but I think also a lot of the research and papers that I see, it is much less common even now to see data that's not squared orthonormal axes. You'll get people kind of bugging out about it if they see data that isn't this way. You'll have reviewers or other researchers kind of look at you and be like, why is your axis not right? Because they're expecting to see it in the orthonormal convention. So half of that was useless, although I did draw on the PowerPoint slide when I was trying to draw. I was actually drawing an aftermath, but you couldn't see it. So yeah, great. We're off to a great start. So you're welcome, everybody. Yeah, can't see anything in aftermath.
No,
now you can, and that was my fault. So I'm very sorry, everybody. And let's continue with this amazing Q&A session that I've severely hindered here. Okay,
it's all good. It's all good.
Man.
So we have a question from Tanae, who I actually met at the College of New Jersey, and they're using some of our equipment and potentiostats, and they're doing cyclic voltammetry experiments. And the question is actually very simple. Either one of us can look at it, but what they're doing is they're taking the first derivative of the data to find peak potentials. And I know that Dr. Prada is he comes from more of a spectroscopy background, so it's very common in spectroscopy.
Is that the PI?
Yeah, that's the PI.
Okay, I'm not sure if I know. Yeah, I don't think I know who that is, but
yeah, he started maybe 1 or 2 years ago. Maybe Tanae can actually.
Is that Tanae's PI?
Yeah, that's Tanae's
okay. So,
PI.
and do you know Tanae and Gio, or just
Tanae? Yeah, I know. I met both of them.
Oh, nice.
Maybe, actually can't remember exactly when I was in New Jersey. Maybe it was in November. It was in November 2022. So they've been doing some work now. But to find peak potentials, yes, you could take the first derivative, and the peak is when the tangent is 0. But I would say most people in electrochemistry find peaks just visually looking at the electrochemistry data.
Or using a peak height tool.
They're using a peak height tool to find it.
I can show some stuff while you're talking.
Yeah,
so go ahead.
absolutely.
Keep talking. I'm gonna share aftermath this time properly.
Yes.
While you talk more about it. But I have some data I'm gonna try to show.
Yeah, most of the time when people are doing cyclic voltammetry experiments, and I'm pretty sure you're looking at a diaryl amine, you have probably some, I'm going to guess, millimolar concentration of the species. You're getting microamps or so of current. The peak associated with an oxidation or a reduction reaction, whether it's multiple electrons, should be pretty relatively easy to see. But you are looking at kinetics data. So I guess perhaps a further question is what kind of experiments are you doing? Are you doing scan rate dependent experiments? And then you're looking at like peak shifts, because I remember some of the data actually looks a little bit like what Neil has with
this is just
voltammograms.
While you're talking, I'll just sort of say what I'm doing briefly. I'm just going to kind of show you both kind of options here. This is just some random RDE data that I did like during my RRDE webinar. It's obviously it's just a simple CV, but there's a peak, so I thought I'd kind of show you while you're talking about that, Alex. But
and Gio's data did look like that, where it was like multiple CVs on top of each other,
right?
Small differences. But yeah, Neil can show the just like the peak height tool. But tonight is this kind of, let's see, we're doing scan rate and concentration dependent experiments. Okay, so
so when you do scan rate concentration dependent, the peak is going to be changing, especially with scan rate. What's that? That's the Randall-Subject equation, right? See, I want to do free slope. I'm just gonna kind of show you. You can get the
Tanae, the question is, if you have a
height.
species are you getting shifts, noticeable shifts in the potential? Because ideally those shifts should be, there shouldn't really be that much change in the potential when you, now maybe when you change the concentration, you might get a little bit possibly, but generally speaking, you shouldn't get too many shifts in the potential.
Yeah. If you get shifts in your potential when you do scans, like you know, let's say, let me change the color thing here. Like if you're doing scans and you get, oh wow, that's not what I want. That's like a highlighter. So if you're doing scans, right, and you do scan rate and you start getting the peak higher or lower, depending on what your scan rate is, you get stuff like this. Okay, great. But if you get faster scans, for example, and it starts shifting this way and the peak starts, you know, moving, that's generally an indication of pseudocapacitance or excuse me, pseudo reversibility. You know, right? Like in theory, you know, based on the whatever the like assuming a perfectly reversible reaction, the peak position is independent of scan rate.
Yeah. And there may be a the shift may also possibly be associated with IR compensation. Like if there's some solution resistance, you can get a little bit of some peak shifting. But all right, so they're introducing pyridine to the system to see a second redox peak. I actually work with pyridine as a graduate student. It's an interesting base. There's a lot of controversy around that molecule for what people were claiming it was doing.
I have not used pyridine.
So pyridine, it depends on the pH of the system, but if you have an acidic solution and you add pyridine to the system, it's a strong base. So it actually attacks and takes a proton. It becomes pyridinium, and pyridinium on platinum electrodes, and actually to a certain degree, a certain extent, like silver and glassy carbon and others, has a can be reduced. But actually, you're just reducing the conjugate acid of pyridine, the pyridinium. It just reduces the hydrogen on the electrode surface. So one thing, I don't know, Tanae, is if that is your system, when you add pyridine to it, what it's actually doing. You see, and seeing our second redox peak shift cathodically. So maybe in Tanae's system, there's a second redox peak that's shifting cathodically.
Well, while you think about that,
Yeah.
I'll just sort of illustrate. Well, I'll mention what I was doing in Aftermath here. You can see the peak height tool, right? It's pretty self-explanatory. So that's one easy way for you to get just that peak height in current. But if you want to do a derivative kind of a thing, you know, in our software, for example, so it depends what software you're using, but you can do, let's see, what is it? Integration and differentiation. So you can differentiate first order with respect to y, for example. We won't replace it, we'll leave it. So this will add a secondary y-axis in theory. So this is giving you, the unit is a little wonky because, you know, technically the derivative of, you know, when you work out the mathematics, this ends up being, I guess, what it's I over current over voltage or something like that, right? So that the units are basically inverse ohms. But anyway, this new trace is the derivative, it's the first order derivative. So this can be done in our software. Some softwares I think can do similar kinds of things too, but there you go. So you can do derivatives, and that can help clarify exactly the peak. Although again, it's the tricky thing with this is that you can see visually the derivative, you know, the derivative is not exactly always going to be equivalent to where the peak is, because the derivative is, you know, at any moment it's the tangent, it's the slope, right? And so this right here is not really the peak. So it depends what you're looking for. You know, you might be looking for the actual max derivative or whatever, and that's fine. But that's basically just where the slope is maximal. the tangential slope, because the derivative is the point slope, right? So this is, you know, smaller, smaller, and then larger, larger, larger. And then obviously right here is where the slope of my trace is largest. And then you can see as it starts to curve this way, the slope is decreasing. So the peak, you know, is not necessarily coincidental with maximum derivative, but if you need the derivative for other reasons, there it is.
Yeah, I asked Tanae a little bit more details about the system. I mean, Tanae's question was really just about determining, okay, is there a better way to find the peak potential? And it's just like using some of these tools like peak height. I like to use the crosshair tool personally.
Yeah,
And they have a wave driver 10, I believe. So all those tools should be accessible. But let's see. Only the second okay. So we got a little bit more information. 1 second. We were assuming ECC mechanism to chemical process. We hypothesize that our doubly oxidized species is first hydrogen bonding, and then the complex undergoes full deprotonation to form pyridinium and the conjugate base of our species.
This is out of my wheelhouse here.
Yeah, I need to think a little bit about this. So it's an electron transfer followed by 2 chemical steps. And those chemical steps, I'm assuming, are they're acid base reactions. Hypothesis are doubly oxidized species. Let's see. Let's see, look at this. Let me think about this a little bit more. Doubly oxidized species is first hydrogen bonding, and then the complex undergoes full deprotonation.
I'll let you think about that while I.
Yeah.
Looks like we got a question from
Yeah,
Fabian. Said we'd like to add several electrodes, anodes, in a solution with various unknown microbes, so that they attach themselves in relation to various applied voltages. Is there an easy to use system? Not one that we make, for example. You know, I don't know that we have a cell that's exactly, you know, designed for something like that. But what you're looking at is something like what you might call a polypotentiostat. These are tricky because the kind of experiment that you're talking about is almost not as common as one where you might use like a multi-channel potentiostat that has like, you know, 10 channels or something like that. And in that case, they all have independent, they're basically, it's just like independent, it's like 10 independent potentiostats. And when you have something like that, you know, you have a bunch of working electrodes, in your case, all of these different anodes, but then you have a bunch of, you know, n number of counter electrodes, one for each, and a bunch of reference electrodes, one for each. What you're talking about doing is really more of like a polypotentiostat. So it's like if you're familiar with a bipotentiostat for like rotating ring disc electrode experiments, it's where you have 2 working electrodes, but 1 counter, 1 reference. So what you're talking about is like 10 working electrodes, 1 counter, 1 reference. It's not like given that there's that like a multi-channel system can exactly operate this way. I think some can, but you know, what you were looking for is a large, and I assume that you're going to put all of these in the same vessel is what you're talking about when you so that's the assumption that I'm making here. But you have some, you know, some vessel with a bunch of microbes in it, and you want to sort of have like almost like cards or baffles. So it's like electrode 1, electrode 2, 3, 4, whatever. And you're going to apply like 100, 200 millivolts, 300 millivolts, 400 millivolts in some cascading fashion to each of them. You just need to have a large enough counter electrode to compensate for the overall surface area of all your working electrodes. So you might need a relatively large counter electrode, and then just one reference electrode somewhere centrally located if you can. Probably what you're looking at in something like this is that there's these kinds of experiments, I should say, are almost always custom kinds of things. Like you're looking at just, like a glass, or I guess it depends on what the compatibility of your microbe system is, but most likely something like glass or, a Teflon vessel. I imagine something like a long, narrow, almost like a bathtub, like a small bathtub where you can sort of just put your electrodes in. I've seen with these kinds of situations, the only thing that might be, I don't know, what you call easy to use. A lot of like, what is it, like pharmaceutical kinds of applications, you'll have the like pipette thing that sort of drops into a bunch of, wells at once and does that kind of thing. Like that's the closest, but that's not really electrochemical in nature as much, right? So I think with situations like this, where you have all of these independent kinds of working electrodes and a lot of, interesting configurations, it usually ends up being a custom kind of a thing. So while I don't think the answer is necessarily no, I'm not aware of a lot of, out of the box sort of easy to use, like you say, systems for a situation like that. I think it's a little tricky. I think most likely you're going to be in the situation of trying to rig something up yourself, which, can be done. And then it's just a matter of finding the right instrument that can accommodate what you're looking to do. Because like I said, it's doable to have, like, if you have 8, whatever, let's just say you have 8 electrodes, to have 8 independent potentiostats or a multi-channel system with 8 channels. But most likely you just want to kind of have one counter and reference, if nothing else, because they'll take up a lot of space. And so if you have a way to gang all of the all of the channels together, excuse me, goodness. If you have a way to gang all the channels together, you'll be able to, you won't have to have whatever 24 different electrodes in your solution. You could just have 8 and then 9, 10, one counter, one reference. It'll save you some space in that way. But again, that's going to depend on the potentiostat you're using, if it has that kind of electronic capability, because not all multi-channel systems can do that. Did you have anything to kind of add about this pyridine? I don't know anything about pyridine, so I have nothing to add.
Yeah, I thought about it. I needed to like think about it.
Yeah, kind of get
today just to conceptualize. So I think maybe there's something maybe I misunderstood, because what you said that you're doing an ECC mechanism, but what you described sounds a little bit more like an EEC. So 2 electron transfers, because you have 2 peaks. So you have 1 electron transfer, 1 oxidation, and then you have the second oxidation. So you're losing 2 electrons, and then you're undergoing a step where, like, all right, now it's deprotonating, and the pyridine is taking the proton to form pyridinium from your forming the conjugate base of your species. That's what, so maybe that was a little bit of the confusion. And I'm assuming that the first electron transfer is, I don't know very much about these aryl pyridine amine systems that you have, but I'm assuming that the first electron transfer is stabilized by a ring. So it's stabilized by, a 5 or 6 membered ring. And then the second electron transfer, the second oxidation, second electron transfer, it gets localized to basically a proton somewhere in your system. So that's what I think. Please let me know if I'm wrong, or if you have some other data. But one thing that you could do, this is just a suggestion, is if your hypothesis is true, you should be able to change the base, pyridine, to other weak bases, and you should notice a change in the reaction rate for the chemical step. Because if you change the strength of the base, ideally it shouldn't react as quickly, depending, of course, also on the scan rate. So that would be another thing you could do to, say, tease out this kind of mechanism. And it makes sense now that, like, okay, it's only happening on the second because of exactly what you said. But I think that's what you're getting at, sort of say. Okay. All right. Do we have any questions? Any further questions? Hopefully,
Yeah, while we wait to see, as in there will be a little bit of a delay from
from
this right now to when you hear this if you're watching, but there were a few questions from Tarek on a community post that we made about this event, so I thought I'd sort of go through those as well. So he had asked, what can a Bode plot tell us that a Nyquist plot cannot? In other words, what is the advantage of the Bode plot over the Nyquist plot? So I guess I don't like this question just from the perspective that it's creating an almighty battle between Bode and Nyquist plots. They're really more complementary, right? And I've talked about this in some of my webinars. I hope that is Aftermath the thing showing this time. Did I do it correctly? I'm not just talking.
Let's see. So
I think
yes,
I just
on
showed
Zoom,
Aftermath.
on my Zoom, I see Aftermath,
Okay.
and then it should show up.
Good. So I'm not going to do another thing where I talk for 20 minutes and people aren't seeing the plot that I'm showing like a fool. Okay. So try to word this in a good way here. So what are you seeing on a Bode plot that you're not seeing on a Nyquist plot? Well, I mean, for one, the obvious answer is the units here that I called the sort of measured quantities. These are the directly measured quantities of your system, and very, very quickly you get an overall measure of the impedance magnet. That's just basically the measured impedance of my system. So, I know that it can be tricky to read a logarithmic plot sometimes, but you can see if I were just opening up a Bode plot like this, and this is all that I saw, I could very quickly get an indication I've got somewhere between 10 to the 2 and 10 to the 3. So somewhere between, 100 and 1,000 ohms of overall impedance. And this is like, 1,000, 2,000, whatever. So something like that. But the point is I can get a quick estimate of my overall impedance. Whereas on a Nyquist plot, I have some indication of that based on the, X and Y axes, but it's a little more convoluted, right? Because real and imaginary impedance are decoupled, calculated kinds of quantities. So you can't just look at exactly what the axis is on your imaginary impedance, let's say, and tell yourself, oh, this is 5 kilo ohms. That's not what that means. That's the Y component of it, right? So the Bode plot gives me a more direct, answer of what's my measured impedance of my system. What is it in general? And then the other thing that it gives you, in the same kind of way that the Nyquist plot, you can look at the features. I have semicircle, I have a, lagging 45-degree Warburg line. I have however many semicircles is how many processes. The Bode plot is a complementary thing because it gives you that same type of information, just in a different way. And typically it's like the number of times the phase angle dips is equivalent to the number of features. And sometimes you'll see one dip or 1-2 dips, like in this case, because the phase angle is usually plotted positively at some companies invert the phase angle. So these peaks would be going up, but so for most people, it's going down. So when I say peak, I sort of mean this negative peak right here. But for however many of those sort of times that the phase angle peaks, dips down, or changes in inflection is an indication of like a different feature that's going on. And that coincides usually with a plateau or a pseudo semi plateau in the impedance magnitude. But really the better kind of point to make is that when you're doing like a circuit fit, for example, you see both of them, right? And so having both visible is really the ultimate goal here, because you know what, just pick any old circuit here or whatever. This one is probably the right one. So it's like ultimately you can see, and in some cases it's like the one of them may fit better than the other, and it's helpful to have both, because you might be able to kind of have a situation where like here, if I'm just looking at my Nyquist plot, I might say, well, that looks pretty good. It deviates a little, but in my Bode plot, I can see clearly that this peak is nowhere near lining up properly. So it's like, if I have one or the other, I'm going to miss how terrible, my analysis is, for example. So that's just one kind of reason to have both. In some ways, I think the Bode plot is really helpful when circuit fitting, because I would say this way, probably more often, I should say, the phase angle is not quite right while everything else might look okay. And so it can help you guide yourself to say, well, I don't quite like how that fits. Everything else looks almost okay, but the phase angle's off. So it'll help you sort of realize you need to keep adjusting some parameters, or, adjust some stuff to get the fit to be where you want it. And that's one of the nice things about having that Bode plot visible, especially when you're circuit fitting, because some software programs just show you one plot. For example, you'll just see the Nyquist plot. You might think you got a great looking fit, but the Bode plot's way off, and you don't know that if you don't see it when you're fitting live. So that's the first one. There's a few other parts of this question, I guess. If you want to interject, Alex, feel free. But
oh yeah, no, I was just gonna say Bode plots are when I was first learning EIS, I found the Bode plot to be a really good like kind of stepping stone. Like, okay, I like Nyquist plots are kind of like an upgraded thing. Just to see like, oh, this is what the potentiostat's physically doing. This is the phase angle, and this is the impedance magnitude. And like that was just easier to conceptually understand before moving to Nyquist plot. But this is a little bit more about fitting.
Yeah, but I think that's a really good point, though. And the reason is that the Nyquist plot is just fundamentally a little more confusing, because it's like real and imaginary. I always try to explain that or show the mathematics of that, but like people still get tripped up. Exactly, like people are used to seeing Nyquist plots, and it's like, oh, that's where the little semicircles and loops are, but it's like, what in the world does this mean? And it's polar coordinates are just sort of harder. Like, I think there must be some psychology behind this. I don't know what it is, but it's like polar coordinates and the whole like vectors and stuff can just be harder to conceptualize. Whereas the Bode plot's more, it's direct, it's what's directly measured. It's just the direct it's just like a cyclic voltammogram, or what, in some sense. It's just as direct as you can get of the most direct is the actual current and voltage versus time sine waves, but
the least is true.
Right. Yeah, exactly. But it's hard to get real analysis from those without doing this. So it's the closest thing you have to the raw data, let's just say. And so, that's a good point to make about it. The question was asked about inverted RDEs. This is a good question. It's also something that I'm just gonna get a blank canvas here. Forget about the Nyquist plot. This is not a Nyquist plot. This is now just a blank canvas. Inverted RDE is a really cool idea. So basically, when you do
move to you're still in aftermath.
I know, I'm just drawing.
Okay, good. All right.
Yeah,
it's just a blank aftermath.
Perfect.
Making sure.
Yes. Every 5 or so seconds, you need to remind me what I'm doing, because I'm apparently liable to just be doing the dumbest possible screen share you can do.
No,
so I hope that I think this is appropriate. Okay, yeah, I just wanted a blank white background or whatever. So if you're doing a rotating disc electrode experiment and you're rotating this thing, you have solution, and then you're vortexing, you're doing your happy RDE experiment. Okay. The problem that can happen is that if a bubble forms here, it gets stuck, right? You're doing HER, you're doing OER, whatever. You get bubbles. Now, often these bubbles will, sweep because the solution's moving and escape. But sometimes you get that situation. It's like the bubble that forms is just like so perfectly dead center that it like won't jostle free. And it's like super, super irritating. And then your electrochemistry day, you might be getting like, oh, I've got my curve. And then all of a sudden, it goes crazy because it's a bubble breaking up the interface and it's all a mess. And you're like, I can't get the bubble away. So I know people, I know some people have that kind of struggle. And one of the solutions, I've seen this once. This is not something that we designed, but a customer that had some of our rotators and electrodes and stuff, they made a thing where they pitched it to at an angle, right? And so they rotated this way. Okay. So this isn't inverted, but it's like, this is like the rotator's at whatever, a 30-degree angle. And so what happens is because it's at an angle here, as long as your vessel is not too poorly like sharp, corners or something like that, you can still get a vortex. You can still get the kind of flow that you're looking for. But if there's a bubble now, because of gravity, of course, it's more likely to escape because it's at an angle. This is harder than you think, actually, to do. That there's a lot. Maybe it's not harder than you think. Maybe you think it's actually quite hard. And if you thought that, you're correct. But the making a rotator is a lot more complicated than it seems like it should be. I mean, it seems like it's a stick and a motor and it just spins. And it's like, well, why is that so hard? It's apparently kind of hard. There's a lot more to it than it seems like there would be, I guess I'd say. It's somewhat non-trivial. And so some of the things that go into that are making sure that when you're, rotating, that it's not wobbling back and forth, right? It's called run out, right? Mm-hmm. And so if you start using an angle, that dramatically increases the chance of run out because now you have uneven torque, uneven force being applied on the shaft, on the motor, on everything. It's not trivial, right? It's actually it's trickier than you think. So the point is that it can be done, but it's not something that we have a ready-made commercial solution for. And then the other part of this question was that he said, well, can I do inverted? What if you do upside? I mean, that's the ultimate, right? If you had the thing upside down rotating, then if there was a bubble, it's just going to escape easily. That's a really cool idea. And there are some companies, I think, that make similar apparatus with this, where you basically have like an inverted, what is this called? Spin coating, right? So there's systems where like spin coating machines, you put like a silicon wafer or something like that, and it's sort of suctioned to this some sort of spindle or shaft, and then there's like some sort of basin to like capture everything. Okay, I'm drawing this a little bit crudely, so go with me for a sec. But it's basically, it's like, you're spraying something onto this surface or whatever, and it's like the excess kind of flows around and just captured in this basin, and this is spinning. Okay. The tricky part about this, of course, well, the easy, I would say easier part of this is that this is like, you might be spraying something, or sometimes you're dripping a solution on while maybe running some kind of current through this or something like that. The tricky thing about thinking of this in a, run out is bad. It's very true, Dan. I agree. The tricky thing about doing RDE in this configuration is sealing everything. It's just fundamentally difficult to seal something that's rotating, especially if it starts rotating quickly. Okay, so if you were to do this stationary, it'd be easier. You could just put some kind of an O-ring, right? Seal around here. You'd have your electrode, some sort of vessel, right? And then you'd have your counter electrode and your reference electrode, and you could do your electrochemistry. But as soon as you start rotating this electrode here, this seal, like the O-ring, would rip apart. That won't probably work very well. There's some trickiness here. So it is also something that we would love to do, but the R&D required is also not trivial. Simply put, we're a small company. We have other stuff we're kind of working on. It is something I would like to offer, to be honest. It would be really interesting to have a really useful commercial solution for inverted RDE, but it's harder than it seems, and it's not something that we have at the moment, unfortunately. I think, Alex, I'll let you take over here.
Oh,
You were going to talk about
well, we got a question from Honest Makamba.
yeah.
Again, very sorry if we are if we're butchering your name. I'll refer to you as Honest. But Honest is asking that, hey, you know, we've read many papers with redox couples, and they just mention kind of randomly that, like, oh, like this is just the number of electrons that are transferred, with no information about how the number of electrons are calculated. And so he wants to know how this is done. So I think there's numerous ways to go about it. But I think it depends. So what I'm gonna do, I'm just gonna share my just kind of a blank PowerPoint. So hopefully everyone can see this. And then under Zoom, I can use the annotate. Not the annotate. Okay. So most of the time, oh, I get the right.
Yeah, it's like a highlighter. I did the same thing. I'm like, oh, that's not gonna work.
Yeah. So most of the time, some people who are doing, say, cyclic voltammetry, you have your voltage, you have your current, and then most of the time it's like you get this duck. And most of the time we'll say this is like a 1 electron transfer process. And there's a couple things that indicate this to us, and it's because there's this 57 millivolt difference between these two. So the peak difference is about 59 millivolts for like a fast electron transfer process. When some people say that there is multiple electrons transferred, if I erase this again, what they're usually, it depends again on the system and the redox couple, but you'll usually see visually there's 1 electron transfer, and then there's like another electron transfer before they go back or something like that. And so this case you have like 1 electron transfer, and then you have your second. I'll actually just put one here, because they're two, like 1 electron transfer, and then at a more oxidizing or reducing potential, you get another electron transfer. So that's a way that people can say, like, okay, there's 1 electron, 2 electrons, 3 electrons, however many electrons. So that's another thing. And that assumes also that like the 2 electron transfers are separated. But the other thing, when I was mentioning earlier about the peak splitting, is that the 59 millivolt peak splitting assumes 1 electron. There is this just n, it's basically n number of electrons divided by 59, you can think of it this way, 59 millivolts divided by the number of electrons transferred. So if there was a 2 electron concerted reaction, then it would be 59, 60 divided, it would be about 30 millivolts would be the peak splitting. But that means 2 electrons simultaneously got like oxidized or reduced at like the same potential, which is in some ways kinetically more thermodynamically unlikely. So that's another thing that people do to determine the number of electrons transferred. They may also do things like, you were mentioning bulk electrolysis as a method. I don't know if bulk electrolysis is really a good method for determining the number of electrons transferred.
This is a really weird kind of a thing, because You know, your question's a good one, but it's almost like it's hard to answer simply for the reason that the number of electrons transferred is usually a thing that people are know, or at least think they know. You know, for example, and it's like when you're using one of these equations, like, you know, Randall-Sepchik equation or control equation or something, it's like there's an n in there, and you put in what you think it is to extract like a diffusion coefficient or something like that. So it's like, well, now you're talking about calculating a thing that the typical procedure is like, well, I know what n is, and I'm using it as, you know, n with temperature and Faraday's constant or whatever other things. So it's like calculating that out is a little bit of a different situation. You know, I think the Tafel slope is one of the ways that that's done. There's some odd assumptions that are built into that, because it technically, like, you know, like when you do Tafel slope calculations, for example, with like Levitch or Kotecki-Levitch studies, it's like it technically is assuming a 1 electron irreversible process or whatever. And it's like, okay, well, if you're trying to figure out how many electrons are transferred, and you're starting from an equation that assumes it has to be 1, and then you're going to measure 2 or 3, it's like, well, you're violating your assumption, although people do it all the time. So it is, you know, it is what it is. But essentially, when there's a similar phenomenon there, and I showed this in my RRDE experiment, but in a similar fashion, that number, that 59 to that 60, you know, millivolts kind of shows up in interesting ways. Actually, you know, with the Tafel slope, for example, 120 millivolts per decade is the number, right? I'm not going to get heavily into a Tafel analysis. I did a webinar on that, but you know, if you get 120 millivolts per decade, it means it's a 1 electron transfer. It's like ideal, or whatever you want to call it, right? That's when you work out the Butler-Volmer equation, you get that. And then basically, if you get 60 millivolts, so don't confuse that with what Alex just talked about. But you know, if you're doing Tafel analysis, this is not peak splitting. It's a different kind of a thing. But okay, so you do Tafel analysis and you get 60. That's over 2. That means it's it's a similar phenomenon. It's like it's divided by n kind of a thing. So it's like, you know, then if you get 40, it means 3 electron. If you get 30, it's 4 electrons. This is done for like oxygen reduction reaction, because you're looking for that 4 electron process when you produce water, compared to a 2 electron process where you produce peroxide. So I know I'm talking through a lot of specific applications pretty quickly here, but you know, Tafel analysis is one way that you can back out the number of electrons. So that is one option, I guess. You know, and in some way you can kind of make a Tafel analysis from anything, but typically rotating electrodes are one way to really do that in a nice, you know, consistent methodology. That wouldn't work probably with bulk electrolysis. You kind of have to sweep a potential in that way, because you're getting, you have to have a logarithmic, you know, current versus potential axis. If you're doing bulk electrolysis, the potential's static. It's not sweeping. So Tafel analysis usually requires you need multiple different potential versus current, like, data points.
Yeah, there's also another thing you can do is simulation. So if you had some simulation software and you fit it to the data, there would be a big difference if it was a 1 versus a 2 versus a 3 electron transfer process.
Yeah. So
that's another thing that people may do. But yeah, no, people in the literature are really bad at explaining how they got the number of electrons. It is just kind of like assumed that, like, oh, it's 1 or oh, it's 2.
Yeah,
it's
exactly.
Like obvious.
And then you have the not bad at explaining, but way too much of explaining, because there's, you know, people will do stuff like mechanistic study analysis, you know, using all kinds of whatever DFT and also all kinds of whatever. But then I always found stuff like that to just be like, this is hard to conceptualize. It's like, okay, so you know, I might have like a 43-step process to describe a 2 electron transfer. It's like, and it's, you know, all these intermediates. And I'm not saying that those are wrong. It's just like, that's that's far in the other direction. You know, I'm just trying to say, like, how many electrons is it? 1 or 2? Great and good. And you're like, actually, there's 4 trillion steps, and there's a couple of those are electron, and some of these are like a thing decomposing, and some of these are radicals. So you go the other way. People kind of like overanalyze their systems and kind of propose pathways and mechanisms and all this kind of cool stuff. I mean, it's interesting, but it can definitely be a bit much, you know, and some of those things also assume, you know, like Alex was talking about with the peak splitting, and, you know, if you get a different amount of peak splitting, or you get different kinds of phenomena with, depending on the number of electrons, all these things are also assuming, yeah, right, like he was talking about, are the electrons transferred like both simultaneously? There's a kinetics component here, right? And so in a lot of ways, what you're working against is the kinetics of electron transfer, which is quite fast. You can't always easily resolve that in a macro time scale, right? And with electrochemistry, you can, you know, the impedance and is the fastest usually, you know, sort of electrochemical technique, because or, you know, pulse techniques or impedance, you're doing like, you know, kilohertz, megahertz, things like that. But otherwise it's like, you know, seconds or milliseconds of sweeping or changing the potential. It's like that isn't fast enough if your process is occurring in microseconds or nanoseconds. So it's like you can't always resolve every individual kind of process that might be happening, right? If they're happening that fast when you're doing electrochemistry, basically.
Yeah, and when they're coupled and stuff like that.
There's a lot of other options that are happening.
Yeah. I mean, people. They may also do just a lot of things to their chemical system to change the conditions of electron transfer as well. But no, that's hey, people are mostly just trying to publish like the thing that is of most interest to them in their papers. And sometimes, the number of electron transfers, it's not obvious. So Honest, I hope that this answers your question. And if you have any follow-up questions, please let us know, or if that was clear, or anything like that. Let's see.
I'll get to one last little thing here. And if there are no other questions, I think we'll probably wrap this up. But there was another part. There's a last part of, and this just sounds like a hardware problem, honestly, but I'll sort of, Tarek was mentioning that doing some impedance, there was some instability, especially in high frequency range, whenever colleagues are using the same potentiostat. So this must be some kind of a multi-channel kind of a system, right? So using a different channel at the same time, his data is bad. But when he's using it and no one else is using it, his data is good. So this really does sound like a hardware issue. You know, using a Faraday cage doesn't make any sense. I mean, it might. You're using a shunt at high frequency, so that's smart. You can kind of get rid of some stuff. But, you know, if the problem is not coming from the reference electrode, if it's not coming from something else, there might be some sort of a shielding issue with the potentiostat itself. You know, in theory, as a multi-channel potentiostat should be n independent channels. You know, they shouldn't interfere with each other unless you want them to. Like if you're doing some sort of a, I don't know, bipotentiostat or whatever kind of an interdependent test. But if they're independent channels, this sounds like a cabling, an electronics, a hardware, some you know issue that like one channel is running, you know, whatever test, and it's impacting the other one. And you know, part of this certainly is a problem because impedance is so sensitive that at high frequency, if there's something to interfere, it's, you know, it's going to interfere. But you want to, that might be something that you know, you need to take up with the manufacturer. Probably. It sounds like a hardware issue primarily to me.
I completely agree. It's like if you have the instrument alone without the other channels being used and it's working perfectly fine, but then when your colleagues are using the other channels and then you do it, you're getting, you know, the same experiment and it's worse. It does sound like a hardware issue. And especially at the high frequency, I mean, we didn't actually have a chance to see the data, the difference. But if you think about the electronics, it's just like, okay, you may have some very, very small inductor that's an electronic component, or all these cables and wires and circuits inside the potentiostat when being used causes some inductance. Well, inductance has like super high impedance at high frequency. So in the high frequency regime, you're getting some stray stuff, even if the inductance value itself is really, really, really small.
Yeah.
So I know Neil and I can also comment, like I sometimes hear our electrical engineers complain about these tiny little things when like, oh, this condition, when you have this condition, there are things that are coupled to each other and they look like they're decoupled, like they're built in the circuit to be decoupled. But then when you actually run it, they're coupled because you're hitting certain instrument limitations, even the component limitations within the instrument. And you wouldn't know this as a researcher, you wouldn't care as a researcher, but like we see from the other side that these things happen, and it's kind of crazy.
Yeah. And not to say, I don't know, that the potentiostat's built improperly, because I don't know whether it is or isn't, but like, there could be some bizarre little electronic interdependency that wasn't anticipated under certain conditions. That's something to contact the manufacturer about, I think.
Yeah, I mean, I've heard some crazy stories about, like, just off topic for those who are interested, like grounding. If you're trying to ground the potentiostat, or float the potentiostat so that's not grounded to like the earth or something, but you tie it to another instrument, and then the electronics from that instrument are connected to like a USB cable to your computer, and that USB cable has a ground line, all of a sudden your potentiostat, which is like, disconnected, is now grounded because of all these little interdependencies. So some of this electronic stuff gets pretty complicated, especially when it's like, oh, I want to do a nano femtoamp experiment.
Yeah, good luck with that.
Yeah, good luck with that.
I hope you have the world's most impenetrable Faraday cage.
Yeah, that's right. That's
and
right.
Like the most floating grounded, system. I worked with a customer like a couple of years ago who was doing similar kinds of things like this, and they, he was using so many different pieces of equipment simultaneously.
Yeah.
And it's like, it's a success story. So thankfully he got successful data, but he was using all kinds of different equipment in this like table with a potentiostat and also a machine that had spatial resolution of some things. To be honest, I don't know 100% of all the other pieces of equipment. I wasn't familiar with like the other, but it was like 90% of his job was troubleshooting to get noise out of it, to make sure that all the equipment were working independently, the other noise sources weren't interfering.
Yeah.
And then finally it was like 10% was like, oh, this is the actual data that I was looking for.
Yeah.
It's like all of it's just troubleshooting, moving things to different locations and all of that. It's not surprising to me that electrochemistry, especially, like, I mean, a lot of science operates this way, but electrochemistry in particular, it's like, it's so much, you'll get 2 years worth of nonsense, and then you finally get like one good data set,
that
and your whole PhD hinges on that 1 week where you got good data. It's like,
oh yeah,
it's a depressing like ratio of output.
I don't know what your experience was, but like for me, like in physical, in a physical chemistry or an analytical chemistry lab, you spend like all your time prepping a sample, aligning a laser, or cleaning electrodes, or all this stuff. And then, once you get the CV, it's like, or the spectra, it's like, well, that was what I needed. And it just took like 2 seconds. Like how fast, if you're doing like 100 millivolts per second over a 1 volt range, it's like,
that's 10 seconds.
10 seconds. Okay.
It's
all right, it's done.
And then it's like another hour of cleanup and
and
polishing and all this stuff. And it's like, oh, I spent 92 seconds getting the data that I need, and I spent 4 hours of prep time, or at least, or whatever. Yeah. As I said, the ratio, don't think about it too much.
Yeah.
It's like, it's depressing. I wish it were a more I wish it was easy to say as researchers that like
Mhm.
everything we do is useful or
I
you
do
know.
believe it though. I do
Well,
believe
yeah, that's the wrong
everything
way
we
to
do
word
is
it.
useful.
It's useful and it just in a different way. Like, you know, you're learning something, which is a useful thing.
Yeah.
And yeah, so much. I mean, it's like that was my grad school. Like I did like 2 to 2.5 years worth of tests that just weren't going anywhere. And it was like the most frustrating thing. And then I switched to like
Yeah.
to studying battery materials, and then I was happy
Mhm.
because batteries are fun.
Yeah.
But it was, you know, it's just depressing after, you know, there's only so much you can take where you just keep banging your head against the wall doing the
Mhm.
same experiment. It's like I did learn a ton, obviously.
Oh, yeah.
I learned
Yeah.
a lot of science and a lot of technique and stuff, but it wasn't like, oh, this is the project and I'm getting results, you know.
Yeah.
But I'm getting the products that I want, or I'm getting whatever. It's like it just
First
nothing
time.
was working in that way. And I was like, I hate this project. I hate everything.
Yeah. Yeah.
That's grad school. That's the real grad school talk. It's not you know, like, oh, I'm gonna change the world and discover some amazing thing. It's like, no, you're gonna just do one very simple, very specified thing for a really long time.
Yeah.
And it may not work at all.
Yeah. Yeah.
So
Yeah.
enjoy.
Enjoy it.
That's grad school.
It's grad school. All right. Well, I think it doesn't look like there are any further questions.